Hello, welcome to my video series of data structures. This is part 3 of Module 5, the tree data structure. In this video, we will introduce the AVL tree. In the previous video, we introduced the concept of the binary search tree, or BST. We explored how BST improved the average case time complexity for search, insertion, and deletion from ON to O log n. This time complexity is based on the assumption that the BST is linearly balanced, which typically occurs when data elements are distributed randomly. However, in the worst-case scenario, where the tree becomes highly imbalanced, the time complexity for these operations can degrade to ON. In this video, we focus on ensuring the O log n time complexity for search, insertion, and deletion operations, even in the worst-case scenario. The solution is intuitive. We ensure that the tree remains nearly balanced. A data structure that achieves this is the AVL tree, named after its inventors Adelson, Velsky, and Landis. The key idea behind the AVL tree is to apply rebalancing operations whenever an insertion or deletion causes the tree to become imbalanced. As a result, the tree is kept nearly balanced all the time, regardless of the orders of data insertion and deletions. It is important to know that the AVL tree is an enhancement of BST. This means that an AVL tree retains the BST property. Specifically, for any node, all nodes in its left subtree are smaller, while all nodes in its right subtree are larger. Let's begin by introducing the AVL property, which the AVL tree uses to detect imbalances. The AVL property states that for every node, the height of its left subtree and the height of its right subtree must differ by no more than 1. In simple terms, this means that the left and right subtrees of each node should have approximately the same height. This property plays a critical role in maintaining the balance of the tree. To illustrate, the tree shown on the left satisfies the AVL property and is therefore a valid AVL tree. In contrast, the tree shown on the right violates the AVL property. Specifically, for the root node 7, the height of its left subtree, represented by the red path, is 3, while the height of its right subtree, represented by the green path, is 1. The difference in height is 2, which breaks the AVL property. As a result, the tree shown on the right is not a valid AVL tree. Now, let's explore how to restore the AVL property when it is violated by the insertion or deletion. It is worth noting that the search operation does not alter the topology of the tree. Therefore, searching in an AVL tree is performed in the same way as in a BST. Let's begin with insertion. When inserting a new element E into a tree rooted at node alpha, one of the 4 cases may occur. In case 1, we may insert E into the left subtree of the left child of alpha. In case 2, we may insert E into the right subtree of the right child of alpha. In case 3, we may insert E into the right subtree of the left child of alpha. Finally, in case 4, we may insert E into the left subtree of the right child of alpha. Know that cases 1 and 2 are symmetric, as are cases 3 and 4. Therefore, we will discuss cases 1 and 3 in detail, as the solutions for their symmetric counterparts follow similar principles. Let's first consider case 1, where the new element E is inserted into the left subtree of the left child of alpha. As illustrated in the figure, the left child of alpha is denoted as beta. Also, denote the left subtree of beta as x, the right subtree of beta as y, and the right subtree of alpha as z. The new element e is inserted into the subtree x. Note that the tree must satisfy the AVL property before the insertion, which can be induced from the base case that trees with a single node are balanced. This insertion may or may not violate the AVL property. For example, the insertion may not change the height of x, or that even if it increases the height of x, it still differs from the height of y by no more than 1. In this case, no rebalancing action is needed. On the other hand, if the insertion does violate the AVL property, it means that the height of x must be increased by 1. Based on this information, we can infer the heights of the subtrees x, y, and z prior to the insertion. Without loss of generality, denote the height of z as k. Now, we claim that y's height can only be k or k minus 1. If the height of y is k plus 1, then the height of beta is at least k plus 2. This will make the height of the left subtree of alpha at least k plus 2, while the height of alpha's right subtree, z, remains k. The difference in height between alpha's two subtrees would then be 2, which violates the AVL property. Since the tree is a valid AVL tree before the insertion, this scenario is not possible and the height of y cannot be k plus 1. Second, if the height of y is k minus 2, then the height of x must be at most k minus 1. This is because x and y are the left and right subtrees of beta, and their heights cannot differ by more than 1. In this case, inserting e into x could increase its height to at most k. Even if the height of x becomes k, the height of alpha's left subtree only increases to k plus 1. Given that the height of alpha's right subtree, z, is k, the difference between the heights of alpha's left and right subtrees will still be 1. This means the insertion does not violate the AVL property, contradicting with the assumption that the insertion caused a violation. Thus, the height of y cannot be k minus 2. In conclusion, the height of y can only be k or k minus 1. Next, we claim that the height of x can only be k before insertion. If x has a height of k plus 1, the height of alpha's left subtree becomes k plus 2. Since the height of alpha's right subtree, z, is k, the difference in the heights of alpha's two subtrees becomes 2, violating the AVL property. This contradicts with the fact that the tree is a valid AVL tree before insertion. Second, if x has a height of k minus 1, the insertion of e can at most increase its height to k. As we previously discussed, even if x height increases to k, it will not trigger any AVL property violation, contradicting with the assumption that the insertion leads to a violation. Therefore, the height of x before insertion can only be k. In summary, before the insertion, the height of x is k, the height of y is either k minus 1 or k, and the height of z is k. If the insertion triggers an AVL property violation, it implies that the height of x has increased by 1. Therefore, after the insertion, the height of x becomes k plus 1, the height of y remains either k minus 1 or k, and the height of z remains k. After determining the heights of the subtrees, we also need to consider the values of the data elements stored within them. Recall that an AVL tree is also a binary search tree, meaning that it must satisfy the BST property. Since X is the leftmost subtree, the elements in X are smaller than both beta and alpha. As Y is in the right subtree of beta, but the left subtree of alpha, elements in Y are greater than beta and smaller than alpha. Finally, Z is the rightmost subtree. Its elements are greater than both alpha and beta. The rebalancing operation to address this case is called a rotation, which rotates beta and alpha clockwise. After the rotation, beta becomes the new parent of alpha. Since each node can have at most 2 children, beta's original right subtree, y, is reassigned as the left subtree of alpha. Subtree x remains the left subtree of beta, and subtree z remains the right subtree of alpha. Let's verify that the rebalancing operation restores the AVL property. The rebalanced tree is shown on the right. Recall that after the insertion, the height of x is k plus 1, the height of y is either k minus 1 or k, and the height of z is k. Now, for node alpha, its left subtree y has a height of either k minus 1 or k, and its right subtree z has a height of k. Since their heights do not differ by more than 1, the AVL property is satisfied at node alpha. For node beta, its left subtree, x, has a height of k plus 1. Its right subtree, one level higher than z, also has a height of k plus 1. Hence, the AVL property is also satisfied at node beta. Taken together, the rebalanced tree is a valid AVL tree. Next, let's verify that the BST property is preserved after the rebalancing operation. Observe that alpha is now in the right subtree of beta, consistent with the fact that beta is smaller than alpha. X is the left subtree of beta, consistent with the fact that elements in X are smaller than beta. Y is in the right subtree of beta and in the left subtree of alpha, consistent with that elements in Y are greater than beta and smaller than alpha. At last, Z remains the rightmost subtree after rebalancing, consistent with that elements in Z are greater than both alpha and beta. Hence, the rebalanced tree maintains the BST property. Next, let's consider case 2, where we insert a new element E into the right subtree of the right child of alpha. Note that this case is symmetric to case 1. Hence, we perform an anti-clockwise rotation to rebalance the tree. After the rotation, beta becomes the new parent of alpha, and y is reassigned as the right subtree of alpha. Subtree z remains the left subtree of alpha, and x remains the right subtree of beta. Since this operation is completely symmetric to the rebalancing operation in case 1, it is straightforward to verify that it restores the AVL property while preserving the BST property. Then, let's consider case 3, where we insert a new element E into the right subtree of the left child of alpha. Denote the subtree rooted at gamma as T gamma, highlighted by the purple shading. In other words, the new element E is inserted into T gamma. If the insertion does not violate the AVL property, no further action is required. Otherwise, the insertion increases the height of T gamma by 1, causing an imbalance that needs to be corrected. Now, let's determine the heights of the subtrees before the insertion. Let the height of subtree D be k. Then, the height of subtree A must be either k or k minus 1. If the height of A is k plus 1, the height of alpha's left subtree becomes at least k plus 2. Since the height of alpha's right subtree D is k, this results in a height difference of 2, violating the AVL property. If the height of A is k minus 2, the maximum height of T gamma can only be k minus 1, as both of them are the subtrees of node beta. Even if the insertion increases the height of T gamma to k, it won't be able to trigger an AVL property violation since alpha's left subtree only has a height of k plus 1. At last, the height of T gamma can only be k. If the height of T gamma is k plus 1, the AVL property is already violated at node alpha before the insertion. If the height of T gamma is k minus 1, the insertion won't be able to trigger any AVL property violation, leading to a contradiction. In summary, prior to the insertion, the height of D is k, the height of A is either k or k minus 1, and the height of T gamma is k. Recall that when the insertion violates the AVL property, it increases the height of T gamma by 1. In this case, after the insertion, the height of D remains k, the height of A remains k or k minus 1, while the height of T gamma is increased to k plus 1. Given that the height of T gamma is k plus 1, the height of B and C can each be either k minus 1 or k, but they cannot both be k minus 1 at the same time. However, as we'll demonstrate later, this detail does not impact the validity of the rebalancing operation. Next, let's determine the values of the elements stored in the subtrees based on the BST property. Since A is the leftmost subtree, its elements are smaller than all of alpha, beta, and gamma. Subtree B is in the right subtree of beta, but also in the left subtrees of alpha and gamma. Therefore, the elements in B are greater than beta, but smaller than alpha and gamma. Subtree C is in the right subtrees of beta and gamma, but also in the left subtree of alpha. Thus, the elements in C are greater than beta and gamma, but smaller than alpha. Finally, D is the rightmost subtree, so its elements are greater than all of alpha, beta, and gamma. To restore the AVL property in case 3, we need to perform a double rotation. First, we rotate gamma and beta anti-clockwise, making gamma the new parent of beta. Then, we rotate gamma and alpha clockwise, making gamma the new parent of alpha. After the double rotation, gamma becomes the parent of both beta and alpha. Beta becomes the parent of subtrees A and B, and alpha becomes the parent of C and D. Now, let's confirm that the rebalancing operation successfully restores the AVL property. Recall that before the double rotation, the heights of A, B, and C are either k or k-1, while the height of D is k. After the double rotation, the subtrees A, B, C, and D are all reorganized in the same level. Given their heights, it is straightforward to verify that the difference between each node's left and right subtrees do not exceed 1, ensuring the AVL property. Next, let's confirm that the rebalanced tree satisfies the BST property. First, subtree A remains the leftmost subtree, consistent with the fact that its elements are smaller than all of alpha, beta, and gamma. Similarly, subtree D remains the rightmost subtree, consistent with the fact that its elements are greater than all of alpha, beta, and gamma. Subtree B is only in the right subtree of beta, consistent with that its elements are only greater than beta. At last, C is only in the left subtree of alpha, consistent with that its elements are only smaller than alpha. As a result, the double rotation for case 3 restores the AVL property while maintaining the BST property. Lastly, let's discuss case 4, where we insert a new element E into the left subtree of the right child of alpha. Recall that this case is symmetric to case 3. In this case, we rebalance the tree using double rotation in the opposite direction compared to case 3. That is, we perform a clockwise rotation between gamma and beta, followed by an anti-clockwise rotation between gamma and alpha. After double rotation, gamma becomes the new parent of alpha and beta. Alpha becomes the new parent of D and C, and beta becomes the new parent of B and A. Now that we have discussed how to rebalance the tree in 4 different cases, we'll present their implementation details. First, since tree heights play a critical role in determining which case applies during rebalancing, we need to include a new member, height, into the tree node object. This member will keep track of the height of the corresponding node. This modification is shown on line 6 of the code. This rotate left function implements the single rotation operation used to handle case 1. The parameter t represents the node alpha discussed earlier. The dashed pointer to node t indicates a connection from the parent of t, representing the case where the tree being rotated is part of a larger tree. To perform a single rotation in this case, we first create a pointer TL to reference the left child of t, as shown in line 3. Next, in line 4, we update the left child of t to point to the right child of TL. This operation reassigns y as the left subtree of t. Then, in line 5, we set the right child of TL to t, making TL the new parent of t. In lines 6 and 7, we update the heights of t and TL to reflect the changes in the subtree topology. These updates are purely for maintaining accurate height information and do not alter the tree topology. Finally, in line 8, we replace t with TL. This step implicitly connects TL to the rest of the tree, making TL the new root of the subtree. Now, we can redraw the nodes and the subtrees to match the view of the tree after the rebalancing operation for case 1. Next, we have the rotate right function, which handles the rebalancing for case 2. The implementation is symmetric to the rotate left function. In line 3, we create a pointer tr to reference the right child of t. In line 4, we update the right child of t to point to the left child of tr. This operation attaches subtree y as the right subtree of t. In line 5, we set the left child of tr to t. In lines 6 and 7, we update the heights of t and tr to reflect the changes in the subtree structure. Finally, in line 8, we attach tr to the rest of the tree, making it the new root of the entire subtree. We can rearrange the nodes of the resulting subtree and verify that its topology is as expected. Next, we have the double rotate left function, which implements the double rotation operation for rebalancing case 3. We can implement the double rotation functions efficiently by leveraging the previously implemented single rotation functions. In line 3, we call the previously implemented rotate right function to rotate the left child of t, referred to as TL, and node gamma. Then, in line 4, we call the previously implemented rotate left function to rotate t and gamma. Similarly, we have the double rotate right function, which implements the rebalancing operation for case 4. In line 3, we called the rotate left function to rotate the right child of t, referred to as tr, and node gamma. Then, in line 4, we called the rotate right function to rotate t and gamma. It is important to observe that all 4 rebalancing operations require only a constant number of pointer adjustments, regardless of the size of the tree. As a result, all 4 functions, rotate left, rotate right, double rotate left, and double rotate right, run in constant time O1. Next, we have a wrapper function, balance, which integrates all 4 rebalancing cases. The function checks the heights of the subtrees to determine which case of AVL property violation has occurred. Based on this information, it selects the appropriate rebalancing operation. For example, in line 4, it checks whether the imbalance is caused by a deep left subtree. If yes, it means that the insertion occurs in the left subtree of t. Then, in line 6, it compares the heights of the 2 subtrees of the left child of t. If the left subtree is higher, the insertion must occur in the left subtree of the left child, corresponding to case 1. On the other hand, if the right child is higher, the insertion must occur in the right subtree of the left child, corresponding to case 3. The use of subtree heights to determine the specific case allows the balance function to handle imbalance caused by both insertion and deletion operations, even though the cases were originally derived from the insertion scenarios. This is because the AVL property is defined by the difference between the heights. In this case, inserting a new element to one subtree has the same effect in height difference as deleting an element from the opposite subtree. As a result, the balance function applies seamlessly to both insertion and deletion scenarios. Using the balance function, we can modify the insert function to ensure that it always maintains the AVL property. Specifically, in line 11, we call the balance function to rebalance the tree after inserting the new element. Note that the balance function only requires constant time, because all 4 rebalancing operations require constant time. Therefore, including the function will not increase the time complexity of the insert function. Similarly, in the remove function, we call the balance function at line 14 to restore the AVL property if necessary. It is important to know that the insertion and deletion operations are implemented recursively, with the balance function being called after the recursive calls. In this case, the function first traverses the tree top-down, locating the appropriate place to insert or delete. After making the action, it rebalances the modified subtree bottom-up along its returning path to the root. In summary, we introduced the AVL tree in this video. An AVL tree is a nearly balanced binary search tree maintained through 4 rebalancing operations. All 4 operations run in constant time O1 and are integrated in every insertion and deletion operation. The insertion and deletion operations with rebalancing ensure that the tree is always nearly balanced, regardless of the data distribution. The balanced AVL tree structure thus guarantees the O log n time complexity for search, insertion, and deletion operations, even in the worst-case scenario. Thank you for watching, and see you next time.